Dear students, in this lecture we will talk about X-ray diffraction or XRD. X-rays discovered in 1895 by German physicist named Röntgen made discovery while experimenting with the electron beam in gas discharge tube, which is also called as cathode ray tube. Röntgen noticed that fluorescent screen in his lab started to glow when electron beam was turned on. Fluorescent material normally glow in interaction with electromagnetic radiation. Röntgen tube was surrounded by heavy black cardboard. Röntgen assumed that this would have blocked most of radiation. Röntgen named these radiation as X-rays. Here X stands for unknown. This is the first ever X-ray diffraction photograph of human bone. This is the diffraction from Frau Röntgen's hand. She was the wife of Röntgen. When Röntgen exposed her wife's hand in front of tube, he saw the photograph of her hand bones and ring projected on the fluorescent screen. Further experiments revealed that this new type of radiation was capable of passing through soft tissues of body but left the bones and metal visible. So these different diffracted X-rays from the bones and metals allow us to know the internal structure of bone, internal structure of materials. This was the revolutionary discovery which revolutionized the medical science. Röntgen was awarded first Nobel Prize in Physics in 1901 for his discovery of X-rays. In 1912, Louis invented the X-ray diffraction by performing copper sulfate polycrystal diffraction. This was the first X-ray diffraction experiment which was carried out by von Leeuwen using the continuous X-ray spectrum and geometry of crystal. He exposed the crystalline material to X-rays and observed the diffracted X-ray pattern on the fluorescent screen. He obtained the picture containing the pattern of spots, each of which correspond to the coherent reflection of X-ray beam from one set of crystal planes. What is X-ray diffraction? Most of the materials are made of very small crystals, and each of these crystals are made of regular arrangement of atoms. Each atom consists of nucleus surrounded by a cloud of electrons which are revolving around the nucleus in different orbits. So the story of X-ray diffraction begins from here. Since the wavelength of X-rays, that is lambda, is similar or equal to the distance d between the atoms in the crystal. As in the crystalline material, the atoms are properly arranged with equal distance from one another, and distance between two atoms, that is d spacing, is equal to the wavelength of X-rays. Louis recognized that X-rays would be scattered by atom in a crystalline material if there is similarity in the spatial scale, that is, if the wavelength of X-rays and intra-atomic distance are approximately same. Then the diffraction pattern which reveals the repeating atomic structure can be formed. Diffraction pattern or pattern of scattered X-rays can be related to the structural arrangement of atom in the crystal. The phenomenon known as diffraction can be used to determine the distance between two atoms in the crystal. When X-rays interact with each other, it results in interference. Here you can see that when two waves, that is, one wave is of blue color and other is of green, when these two waves interfere with each other and resulting wave is the red color wave, you can see that if the waves are in alignment or in phase, the net interfered signal is amplified or constructive interference. That is, when two waves are in phase, these waves will reinforce each other and result will be the amplified wave, and the resultant interference is the constructive interference. Here you can see that when green and blue waves come in phase, that is, then we get the resultant wave of bigger amplitude. If the waves are aligned out of phase, the net signal is destroyed and it is known as destructive interference. That is, here you can observe that when two waves come like this out of phase, then the resulting wave will be resulting interference will be the destructive interference, and these out of phase wave will cancel the effect of each other. When X-rays incident on the atom, its energy is absorbed by the electron. The electron occupies the discrete energy states around the atom. This is not enough energy for the electron to release. The energy must be re-emitted in the form of new X-rays, have the same energies as an original incident X-rays. This process is called as elastic scattering. In elastic scattering, incident X-ray energy is equal to the emitted X-ray energy. This indicates that the path difference between the incident and diffracted beam of X-rays are basically demonstrating the d-spacing or distance between the two atoms in the parallel different lattice plane of crystal system. These are the regular arrays of atoms within the crystalline material, and this distance d between two atoms within the crystalline is of order of the wavelength of incident X-rays. So, the regular array of atoms should behave much like an optical diffraction grating. Just as there is a relation between slit and wavelength of light in the grating, there will be a similar relation between lattice spacing of the crystal and X-ray wavelength. As we can see in the figure that there are horizontal rows. These two rows representing the planes of crystal, a collimated beam of X-rays, that is A and D, when these beams are directed at the surface of crystal and making an angle theta with the surface of crystal, and X-ray will interact with the electron of crystal lattice and will be scattered. Some will suffer a change in frequency, that is Compton scattering, and thus will be lost from the coherent beam. But most of the photon in the region of few kilo electron volt quantum energy are scattered without change in frequency. Since the electron in the crystal belongs to the lattice atom which are arranged in proper order. That is, here you can see atoms are arranged in proper manner, so coherent scattering is absorbed. When the two rays diffracted and interfere constructively, that is, here you can see that when two waves, coherent waves which are in phase, interfere with each other constructively, we get the maximum diffraction when path difference between two rays is integral multiple of wavelength. This condition is also known as Bragg's law. Bragg's law can be explained from this figure. The D is the spacing between two atoms or lattice point in the crystal, and it is equal to BE. Here you can see in this figure that this one is atom in this crystal plane and this one is atom in the lower crystal plane, and this is the distance D between two atoms, and it is equal to B and E. The path difference between two incident and diffracted X-rays A, B, C and D, E, F. As here you can see that these A, B and C. These are the two incident and diffracted rays, that is D, E, F. And these are the incident diffracted rays, and the path difference between these two rays is equal to GE plus EH. Here it is represented in the figure. This is equal to GE plus EH, and it is equal to 2D spacing of crystal. In triangle GBE, here you can see that this is the triangle GB and E. Here the GE by BE, this is equal to the sine theta. So we can say that GE will be equal to BE sine theta, and this distance GE equal to BE equal to D. So we can say that GE is equal to D sine theta. Again, in the triangle, that is in this triangle BEH, or in the triangle EHB, we can calculate the sine theta, which is equal to EH by BE. Here again BE is the distance between two atoms. By placing the D instead of BE, we get that BE sine theta is equal to D sine theta. So the path difference, putting the value of GE plus EH, we get D sine theta plus D sine theta is equal to 2D sine theta. So the distance between 2D spacing is equal to 2D, part difference is equal to 2D sin theta. This condition is also known as Bragg's law. This is the fundamental relation used in X-ray analysis to measure the crystal spacing. So the conclusion is, if the path difference BD is equal to 2D sin theta is equal to the integral multiple of X-ray's wavelength, then the diffracted X-ray beam will cause constructive interference. That is, we can say that when 2D sin theta, that is path difference, is equal to n lambda, is the condition for constructive interference. Hence, the intensity of diffracted X-ray will be maximum. So, we can say that the maximum intensity corresponds to the constructive interference of diffracted X-rays. That is, n lambda is equal to 2D sin theta, where n is equal to 1, 2, 3 and so on. So this is known as Bragg's law. What are the uses of X-ray diffraction? We can use the X-rays for crystal structure, for the analysis of crystal structure, for phase and composition of material, for crystal size and strain in materials. We can observe the defects in crystal with the help of X-rays, and we can also observe the texture of the crystal, orientation, unit cell parameters A, B, C and lattice symmetry. We can identify the amorphous material with the help of X-ray.